Right, so currently sharing my screen, so maybe you can confirm if you're able if you're able to see the screen, and if you're able to get what I'm saying, so that we can continue with our discussion. Are you able to get what I'm saying? Yeah. Right. So maybe before I move to something else, let me just allow myself to go back to this slide here, and let's look at what happens when n is equal to 1. Let's look at what happens when n is equal to 1. Here, look, we are saying n is greater than or equal to 1. Maybe let me just allow looking for this part, view, add, like so, right? And back to the board. Now let's look at what happens when n is equal to 1, because here I'm saying, if you look at this part of the definition, I'm saying n has to be greater than or equal to 1. But then what happens if n is equal to 1 here? What happens if n is equal to 1? What is going to happen to this formula, and what can be what is going to be the meaning, in other words? So if n is equal to 1, then we know that, for example, some vector u, the formula here is I is equal to 1 up to n, and then the formula is that we have lambda e, and then we have ve, like so. So if n is equal to 1, then there's only one item in this sum. There's only one item in this one, in this sum, because we go from 1 to 1, which is only having one item. So we have lambda 1, and then we have v1. What this means is that the two vectors u and v1 are collinear, because they are collinear. So here we are scaling the vector u by some scalar lambda 1. So if n is equal to 1, then the two vectors u and v1 are going to be collinear. U and v1 are going to be what? Are going to be collinear. And of course, I'm sure the spelling might be wrong, but of course, at least you can hear what I'm saying. So if n is equal to 1, then the vectors u and v1 are going to be what? The vectors are going to be collinear. Now, let me give you guys an example. Let's look at an example here, a very interesting example. Now, do you think, let's say we have some vector u, which is equal to 2, 1, and then we have some vector v, which is 1, 1. So do you think these two vectors are collinear? So who can justify, if at all you can see what is happening here? Are the two vectors collinear? And how can we go about sort of like answering this particular problem? How can we go about answering this problem? Are the two vectors u and v collinear? Okay. So anyone who wants to try? Anyone to try? Okay. Wiza, how do we go about verifying or maybe checking if the two vectors u and v are collinear? So using what I've written here, if the vectors u and v are collinear, maybe let's just solve it together. If the vectors u and v are collinear, so let's suppose that u and v are collinear. Suppose u and v are collinear. So let's suppose that the two vectors are going to be collinear, like so. So suppose that u and v are going to be collinear. Well, if u and v are collinear, it means the vector u is going to be equal to lambda. Then we can find some lambda. This is going to imply that we can find some lambda in this case, let's say r, like so. Telke, we can find such that u is going to be equal to lambda multiplied by v. Now u in this case is 2, 1, like so, and then lambda, and then v is 1, 1, like so. Now let's maybe go down a little bit. So let me just write the vectors in column form so that we see what is happening here. So 2, 1, and then lambda, and then 1, 1, like so. So here we have 2, 1, like so, and then this is going to be equal to lambda, lambda, like so. Oh, we know that two vectors are equal if and only if their corresponding components are what? Are equal. So in this case, lambda is equal to 2 and lambda is equal to 1. But then this is a contradiction because we cannot have two values for lambda. We cannot have lambda is equal to 2 and lambda is equal to 1. So this is a contradiction. So it means that these two vectors are what? These two vectors, u and v, are not collinear. U and v are not collinear because we cannot have it doesn't make sense to have two values for lambda. So u and v are not collinear. Whatever the spelling is, at least you're able to get what I'm saying. Okay, so u and v in this case are not collinear because we cannot have two values for lambda. Lambda is equal to 2 and lambda is equal to 1, so it doesn't make sense. Okay, so these vectors u and v are not what? Are not collinear. Remember, let me just go back here. When we're talking about the definition for an espace vectoriel, we said you're supposed to go through, all these 8 properties. If you want to verify that the given set is an espace vectoriel, you have to verify all these 8 properties. But then I told you that we'll be able to shorten these 8 properties to 3, to at least 3, maybe 2. It depends on, your choice of. We'll talk about the equivalent meanings of the definition you're going to see for a sous-espace vectoriel. We'll look at other equivalent meanings or other equivalent descriptions. However, we'll be able to shorten all these things. So let's look at the definition of a sous-espace vectoriel. So soit E, un cas espace vectoriel, une partie f de E. So we give ourselves some subset f of E. So here we have E, which is an espace vectoriel. So here E is an espace vectoriel, vectoriel, and then F is a subset of E. F is a subset of E, and then F is going to be known as a sous-espace vectoriel. F is going to be a sous-espace vectoriel of E if F satisfies the following 3 conditions. Okay, F is going to be a sous-espace vectoriel if F satisfies let me just allow someone to join like so. Okay, maybe go back to the board like so. Now F, which is a subset, a subset of E, is going to be a sous-espace vectoriel. F, a subset of E, is going to be a sous-espace vectoriel of E if it satisfies these 3 properties. Now the first property here says the zero element of F, the zero element of E, which is l'élément neutre. Remember, when we were talking about the 8 properties, we saw that E is an abelian group, and then there's what is known as l'élément neutre, or the identity element. But here we are saying the first property, the first thing that we're supposed to check is the zero of E part of F. So if this is true, then F has to be non-empty. Okay, F has to be non-empty. So what does it mean for F to be non-empty? It means F has to have at least some element. So if you want to verify or to show or to check this property that we have here, you must verify or see or find out if the identity element of the parent espace vectoriel, which is E, if the identity element of the parent set is in F. If the identity element of the parent set is in the child set, which is F, then the first property would have been verified. And then the second item here, or the second property here, is simply saying there must be stability with respect to what? With respect to addition. Now the third property here means that we must have stability with respect to what? With respect to scalar multiplication. So here, these 2 properties are about stability. Stability, meaning stability with respect to addition. It means if I get any 2 elements of the set F and I add those 2 elements of the set F, I'm going to get an element that is in the set F. Then the third property is also about stability, but with respect to what? To scalar multiplication. if I multiply some scalar lambda by some element x of f, and then I must get back this. This. So I must get back lambda multiplied by. I must get back some result that is also going to be in the set f. Now this definition, or this what I've written here, the three properties that I've written here, everything I've written here is also equivalent to. First of all, point number one, you check that the f is non-empty, which means you have to verify that the identity element of the parent set is in the child set, which is f, like so. And then we can combine the second property and the third property and say, quel que soit alpha et beta in K, like so, and quel que soit x, y, so we can just say quel que soit x, y. Now two elements in what? In E. We can shorten these two properties and say they are combinaison linear. The combinaison linear of these two elements, x and y, has to be in E. So alpha plus x plus beta. Let me just clear this. So alpha plus x plus beta y. The combinaison linear of these two vectors x and y has to be in E. We can shorten these two properties to this. Okay. So in case it's not really clear, maybe let me just write it in a better way. So we can combine these two properties here and say quel que soit alpha et beta, two scalars in K, like so, and then quel que soit x, y, two elements of what set? Two elements of f, like so. Well, we must have that their combinaison linear, which is alpha x plus beta y, has to be an element of f, like so. So if we have a set that is going to satisfy these three properties, then it is going to be a sous-espace vectoriel. And then if some set f is a sous-espace vectoriel of another espace vectoriel, automatically it is going to be what? It is also going to be an espace vectoriel. A sous-espace vectoriel is also an espace vectoriel. So if you want to show that some vector f is, that some set f is an espace vectoriel, all you have to do is to show that f is a sous-espace vectoriel of another espace vectoriel. Maybe let me just write that as a comment. Let me just write that as a comment here. Maybe to say to show that f is an espace vectoriel. To show that f is an espace vectoriel, show that f is a sous-espace vectoriel of another espace vectoriel, like so. So let me just put that as a comment, like so. Maybe let me just move it somewhere here so that you see. So this is how we'll be able to shorten our demonstration or our verification of is some set an espace vectoriel. So instead of going through all the 8 properties, all we have to do is to show that our f is a sous-espace vectoriel of another espace vectoriel. That is the one that we know that this one is an espace vectoriel. For example, R2, for example, we know that R2 is an espace vectoriel. So if I give you some set, and if I show that the set that if you show that the set that I've given you is an espace vectoriel, if you show that the set that I've given you is an espace vectoriel, then if you show that the set that I've given you is a sous-espace vectoriel of R2, and I know that R2 is an espace vectoriel, then that particular set is going to be a what? An espace vectoriel, because a sous-espace vectoriel is an espace vectoriel. So if I want to show that the given set F is an espace vectoriel, I don't have to go through all the 8 properties. Now you can do that if you want, but you just have to show that F is a sous-espace vectoriel of an espace vectoriel, of another espace vectoriel. We'll look at an example so that you guys understand. We'll look at an example. Okay, so if you want to show that some set F, which is a subset of E, which is our parent espace vectoriel, if I want to show that F is a sous-espace vectoriel of E, I have to check the three properties. F has to be non-empty, meaning F has to be non-empty, meaning the identity element of the parent set, which is E, has to be in F. That's what we have to do to check. And then the second property is that we have to have stability by addition. The third property is we have to have stability by scalar multiplication. And then whatever I've written on the left is equivalent to whatever I've written on the right. So what is on the right is sort of like we combine the second and the third property. So meaning the linear combination of two items x and y that I take from my set F is going to be in the set F. Example. Now let's look at an example to understand what is happening here. Okay, maybe, but before we look at an example, let me also mention that any espace vectoriel has two trivial sous-espace vectoriel. So any vector space. So let's say the identity element of E and E itself. The identity element of E and E itself. The identity element of E and E itself are trivial subspaces. Now I'm going to write it in English. Subspaces is sous-espace. The identity element of E and E itself are trivial subspaces. Trivial subspaces of E. So if E is an espace vectoriel, two trivial subspaces or two trivial sous-espace vectoriel of E, we're going to have the identity element of E and E itself. Now you can check. Check. C'est bon? Now let's look at an example. Let's look at an example to better understand what is happening here. So let me create a new page like so, and let's look at an example. So let's say we have E. Here our E is R squared. Let's say our E here is R squared. And then let's give ourselves F, which is a subset of E. And then we have xy, and then R squared like so. And then x plus y is equal to 0. Now, before we even do anything here, let's understand what we have here. So here we have set builder notation, right? If you remember very well, this is set builder notation. So we have F where where if an element is in F, it has to satisfy this condition. So this condition has to be satisfied for us to consider that some element y or some element x is a member of the set F. This condition has to be met. Okay, so F is a subset of E. F is a subset of E. Why is F a subset of E? We can clearly see that here all the elements of F have two components, right? Have two components x and y. All the elements of F have two components x and y. That is what we have here. All the components of F have two components x and y. All the elements of F have two components x and y. And then that is also the case for what? For R2, because all the vectors have two components x and y. But then for an element to be a member of this set F, the sum of these two components has to be equal to what? Has to be equal to 0. So this condition has to be checked if we are to verify that this that some element is going to be part of the set F. So the question here is, montrer que F est un sous-espace vectoriel, sous-espace vectoriel de E. Now, the first thing that we're supposed to verify is that, remember, we're supposed to verify that F is non-empty. Is non-empty. We have to check. So how do we check that F is non-empty? Well, we are supposed to verify that the identity element, that the zero element of E, which is the zero element in this case of R2, because E is equal to R2, is in, we have to verify that the zero element is in what? Is in F. So if you remember very well, the zero element of E, the zero element of R2, the zero element of R2 is the zero vector, which has 0 here and 0 here. Now, is this element a member of the set F? According to you, what do you think? Is this vector 0, 0 a member of the set, or a member of the set F? And then justify your answer. Tasila, is 0, 0 a member of the set F?
Yeah, yes.
Okay, justify.
Because first of all, this condition is satisfied.
Okay.
X plus y is equal to 0. And then, if the parent set is not empty, meaning the subset is also not empty.
Okay, that is correct. That is correct. That is correct. So the parent set, if the parent set is non-empty, then automatically the identity element of the parent set is going to be in the child set, which is F in this case, and so F is not going to be empty. So here we see that there's the 0, 0. Here our X is 0 and our Y is 0. If you plug in these two values here, you see that you get 0 is equal to 0. So the condition has been verified. And so this is we. The answer here is we, because you can see that the condition here is verified, because X here is 0, Y is 0. Plug those two numbers here, and then you see that the condition is true. So let's go to the second property. So what is the second property saying? So we can also go back and check, like so. So the second property is about stability by addition. So we have to take X and Y from F and show that these two elements are in F. Okay? So for the second property, we take two items from F. We take two elements from the set F that satisfy this condition. Now, it doesn't matter what you choose. Now I'm going to say soit. So we can say soit U, that has components X and Y, and V, that has components X prime and then Y prime. And maybe I'm taking U from F because that's what the condition is saying. I take this from F, and I also take V from F. So here I have X prime and then Y prime, like so. I also take it from F. Now what is my goal? My goal is to show that U plus V is going to be in what? Is going to be in F. That is my goal. That is my goal. I want to show that U plus V is in F. So let's first of all calculate U plus V. So we can calculate U plus V. Now, instead of using this first definition that I have here, which is going to be a little bit long, I'm going to use the definition that is on the right. I want to show that if I choose two elements from F, I want to show that, and some scalars alpha and beta, I want to show that the linear combination of X and Y is going to be in F. So I'm going to use the second version. You can use the first one, but then you have to verify the second condition alone and then the third condition alone. But for this one, I'll just allow myself to use the second condition because I want to sort of save some time, and I know that you guys will be able to follow what is happening here. Okay, and then let me also choose alpha, a scalar from R. It doesn't R in this case because we're talking about R squared. So let's just simplify everything and just take alpha from R, and then beta is also coming from R, like so. Now my goal is to show that the linear combination. My goal is to show that the linear combination alpha U plus beta V is going to be an element of the set F. How do I do that? Well, the first thing is to calculate alpha U plus beta V. So we know that alpha U plus beta v is equal to alpha multiplied by x and then y, like so, and then plus beta, and then we have x prime and then y prime, like so. C'est bon? And then this is going to be alpha x, alpha y, like so, and then plus, and then beta x, and then beta y prime, beta x prime, and then beta y prime. Then we can add the corresponding components. So this is going to be alpha x plus beta x prime, and then alpha y plus beta y prime, like so. C'est simple. C'est très simple. So you've calculated this. But then let's go back to this. What does it mean for the vector? What does it mean for the vector u to be in F? Okay? What does it mean for the vector u to be in what? For the vector u to be in F. What does it mean for the vector u to be in F? So for you to be in F, it means the sum of the components is equal to what? Is equal to 0. Because that is what the definition is saying here. Any element of F is satisfying this condition. So here u is in F means, well, this here is going to mean that x plus y is equal to 0. And then v is in F. This is going to mean that x prime plus y prime is equal to 0. Okay? So we want to allow ourselves to use this this definition that we have here. Okay, we want to use this definition that we have here. Okay, so u, I repeat, u is a member of the set F, which means it satisfies this condition that we have here. So it means the components here, x and x plus y is equal to 0. Same thing here, x prime plus x prime plus y prime is also going to be what? Is also going to be equal to 0. Okay, x prime plus y prime, is also going to be equal to 0. So here we've calculated alpha u plus that quantity, like so. Okay, so the goal is to show that this sum is going to be in what? That this sum is going to be in F. So for this sum to be in F, it means now that we are here, okay, let's now, we have this. This is going to act like our x. This component here is going to act like our x. If you want to apply this definition that we have here, and then this one is going to act like our y. So let's get these two items and plug them in this equation, x plus y is equal to 0. I mean, this equation, x plus y. And then let's look at what that is going to be. So let's look at x plus y. So let's look at alpha x plus beta x prime plus alpha y plus beta y prime. Is this going to be equal to 0? That's my question. Is this going to be equal to 0? Well, let's check. Now here, let's regroup the terms. Let's regroup the terms such that the ones with alpha are on one side and then the ones with beta are on the other side. Okay? So here we have alpha x plus alpha y, and then plus beta x prime plus beta y prime. Now, this is going to be equal to, I can factorize by alpha, so I'm going to have x plus y. And then here I can factorize by beta, and then I'm going to have x prime plus y prime. Oh, look, here we've said u is in F, which means x plus y is equal to 0. So this x plus y that I have here is going to be equal to 0. So here I'm going to say alpha multiplied by 0 plus, v is taken from F, which means x prime plus y prime is equal to 0. So meaning here I'm going to have beta multiplied by 0. And then here we'll have 0 plus 0. So we see that this item is indeed equal to 0. So the answer here is oui. This is equal to 0. So we verified all the conditions. Now the conclusion here is d'où F est un sous-espace vectoriel, est un sous-espace vectoriel de quel espace? De l'espace est un sous-espace vectoriel de R2. Like so. C'est très très facile. Okay? So is it clear? Now, Do you think F is an espace vectoriel? Do you think F is an espace vectoriel? Is F an espace vectoriel? We are from showing that F is a sous-espace vectoriel. But is F an espace vectoriel? Is F an espace vectoriel? Is F an espace vectoriel? What do you think, Natasha? Is F an espace vectoriel? Is F an espace vectoriel? Wiza, is F an espace vectoriel?
It is an espace vectoriel.
Then what is your justification?
Okay, my justification is if F is a sous-espace vectoriel, then it is
an espace vectoriel. Très bien, très bien. So that is the case. So F is a sous-espace vectoriel, then automatically is going to be an espace vectoriel. So now let me just change the question. I want someone to help me here. Is this a sous-espace vectoriel of R2? Let me just position myself here. So same question, but I'll change something. Let's say E is equal to R2. And then here, let our F be equal to, the set of elements X and Y that are in R2 such that X plus Y is equal to 1. Now, is F est-il un espace vectoriel? Un sous-espace vectoriel? Est-il un sous-espace vectoriel? Est-il un sous-espace vectoriel? Un sous-espace vectoriel de R2? So, Tassila, what do you think? Is F an sous-espace vectoriel of R2 if F is the set such that X, Y, such that the two items X and Y satisfy the equation X plus Y is equal to 1. Do you think this is a sous-espace vectoriel of R2? Do you think this is a sous-espace vectoriel of R2? Well, no. Okay, you can start by checking the conditions. Is the first condition verified? Is the first condition true? So first of all, no, because you have to see what is the zero element of R2. What is the identity element of R2?
0, 0.
Yeah, it's 0, 0. But then is 0, 0 an element of F? No. Because here, if I plug in 0, 0, if I plug in 0 for X and 0 for Y, 0 won't be equal to 1. So we see that 0, 0 is not an element of F. And because the first condition has been violated, we cannot continue. We cannot check the other two conditions. So automatically, F here is not a subspace. F is not a subspace of what? Of R2. And then car justification here is that the zero element of E in this case, which is equal to the zero element of R2, is not part of the set F1. Let me just call this F1 so that you don't confuse it with the previous example. So if the takeaway here is that if some set F is a sous-espace vectoriel of the parent set, which is E, automatically the zero element of E has to be part of F. If the first condition is violated, automatically we cannot continue checking the other conditions. So we stop. Okay? So if F is a subspace, necessarily the zero element of the parent space has to be part of the set F. So that is how you go about answering these questions. Okay? Is it clear now? Is it clear? Je passe? We look at the theorem. Très bien. Maybe Tassila, you can unmute your mic. Très bien. So let's look at the theorem. So the theorem is saying l'intersection d'une famille non vide de sous-espaces vectoriels est un sous-espace vectoriel. L'intersection d'une famille non vide de sous-espaces vectoriels SEV est un sous-espace vectoriel. So let's say we have a parent space. Let me just maybe tell you what this is saying here. Let's say we have a parent space E, okay? And then we have F, which is a subset of E, and we have G, a subset of E. So we have a parent space. We have the parent space, which is E in this case, and then we have F, which is a subset of E, and G, which is a subset of E. Now, this is saying that if this is a sous-espace vectoriel, so if F is a sous-espace vectoriel and G is a sous-espace vectoriel, then the intersection F intersection G of these two, les deux espaces vectoriels, is also going to be an espace vectoriel. Then the intersection F intersection G is also going to be a SEV. So if we have some parent space which is E, the theorem here is saying that if F, which is a subset of E, is a sous-espace vectoriel and G is a sous-espace vectoriel, then the intersection of the two, les deux espaces vectoriels, is also going to be a sous-espace vectoriel. Now, even we won't write the formal proof here, but let's understand how to go about this proof and why this proof is actually making sense. Let's understand why this proof is making sense, and let's understand that this is actually going to be true. So let's look at the intersection. So I'm going to say, to simplify things, I can maybe just say P, let P be. So you can say let P be the intersection of the deux espaces vectoriels, F and G. Now we know that F is a sous-espace vectoriel and G is a sous-espace vectoriel. Now the first thing that we're supposed to check, is the first condition. The first condition is F intersection G non-empty. Is F intersection G non-empty? Well, the answer here is a quick yes. Why is it a quick yes here? C'est très facile. Look, F is already a sous-espace vectoriel. And then we also know that G is a sous-espace vectoriel. And then if you remember what I said if F is a sous-espace vectoriel, then automatically the zero element of E is in F. Same here, because G is a sous-espace vectoriel, and then the identity element of the parent space is also going to be in G. Or if the zero element is in F and the zero element is in G, it means that the zero element is going to be in F intersection G. So this is going to imply that F intersection G is going to be non-empty. You understand? C'est très facile. Now the second condition is, for the second condition, we're supposed to verify or prove. For this one, I'll use the first definition. I'll check stability for addition and then stability for scalar multiplication. So let's look at two. Let's give ourselves two items, x and y, from the intersection. So let's say we have, so quel que soit x, y from the intersection f intersection G. So here, let me just get rid of this p here. I actually don't need it. So, and this word here and this here. So let's get any two elements from the intersection. So if x and y are in the intersection, if x and y are in the intersection, it means that x is in F and y is in F, and then it also means that x is in G because they're in the intersection. X is in G and y is also in G. This is what it means. Okay, this is what it means. So we've taken two elements, x and y, from F intersection G. Okay, we've taken two elements from x and y. So what do you think is x plus y? excuse me, is x plus y in f. Is x plus y in f? Now the answer here is also a quick yes. Now why is it a quick yes? Let's understand. The answer here is a yes because look, f here is a sous-espace vectoriel. Same thing here, G is a sous-espace vectoriel. It means f is stable with respect to addition and G is also stable with respect to addition. Because both, these two items are in both sets, that is f and g. If I take the sum of x plus y, then automatically x plus y is going to be in, so here let me just follow it. So x plus y is going to be, so here is f intersection, x plus y is going to be in f automatically because x and y are both in f, and then f is stable, is stable with respect to addition because it is a sous-espace vectoriel. And then the same thing x plus y is going to be, the same thing x plus y is going to be in G because x is in G and y is in G. G is a sous-espace vectoriel. We have stability by addition. So x plus y is going to be in G. Oh, look, x plus y is in F and x plus y is in G. Now this is going to imply that x plus y is going to be in the intersection F intersection G. Now I'll leave the third property for you guys to check. It's also simple. Just use the fact that f and g are going to be subspaces. Just use the fact that f and g are subspaces. Then you'll be able to prove this theorem. So you see that it's very simple to show. So if we have two subspaces f and g, then the intersection of f and g is also going to be a sous-espace vectoriel. Now if you are curious, you are wondering, is the union also going to be is the union of two subspaces going to be a subspace? Well, in general, the answer is going to be no. Now for that, I can give you a counter example. For that, we can look at a counter example. So where did I write the counter example? L'intersection, très bien. Well, I actually duplicated the slide here, so I'm just going to get rid of this one. So let's look at the counter example. The union is not true for the union in general. I'm saying in general. We can have some cases where it works, but in general, la réunion de deux sous-espaces vectoriels n'est pas forcément un sous-espace vectoriel. So the union of two subspaces is not necessarily a subspace. So here they've given us a counter example. Let's look at this counter example and understand what is happening here. So they've given us the set F1. The set F1 such that we have where all the elements are looking like this, 0, y. So members of this set are elements like, for example, 0, 1, for example, 0, 2, for example, 0, 3, 0, 4. You only change the y, but then the x is fixed at 0. So they also give us another one, which is F2, where now this one, we fix the y, and then it's only the x value that is changing. So these are subspaces. You can verify, check. It's easy to verify that these two spaces are what? Are subspaces of R2. Okay, let's verify. Is F1 non-empty? Yes, it's non-empty. Because if I choose y is equal to 0, I'll find the identity element of R2. So I see that F1 is non-empty. Same, if I choose x is equal to 0 for F2, I'll see that F2 is going to be what? Non-empty. Then we'll also have stability by addition and stability by scalar multiplication. You can verify now that you understand what you're supposed to do. But I'm going to tell you straight away that F1 and F2 are subspaces of R2. Now, is the union a subspace? On va voir. So let's look at what is written here. So here they've told us the answer that F1 union F2 is not a sous-espace vectoriel. And then this is their justification. So here they've chosen a specific element. That's what it means, choosing a counter example. You have to find a specific, remember we talked about different ways of proving things, of proving theorems or propositions. We talked about par contradiction and then par contraposé, contre-exemple. This one we're using contre-exemple. So we've picked a specific element of F1. In this case, it is 1, 0. We've also picked a specific element of F2, which is 0, 1. You can see that this 1, 0 is actually an element of F1 because we can see that, they actually swapped here. 0, 1 is a member of F1. 0, 1 is a member of F1 because here the X is fixed at 0. The Y is changing. So 0, 1 is actually a member of F1 and then the other one is a member of F2. So here, doesn't matter, but let's choose, if you take these two examples, U and V here, let's look at their sum. Let's look at their sum. Let's check the conditions. Let's check the conditions. So here we're checking the second condition. Do we have stability by addition? Do we have stability by addition is the question we're asking ourselves here. Well, let's look at U plus V. If you look at U plus V, you see that U plus V will give us 1, 1,1. Oh, this is a problem because 1,1 is not in F1. It is also not in F2, and so it cannot be in the union, because if some element is in the union of two sets, it means it is in at least one of these sets. That's what it means. X is in the union of A and B. It means X is either in A or X is in B. But here X is neither a member of F1 nor a member of F2. And so it cannot be a member of F1 union F2. And so we see that there's no stability here. Okay, there's no stability here in general. And so the union of two subspaces in general is not going to be a subspace. The union of two subspaces is not going to be a subspace. C'est clair? Je passe? So the takeaway here is this. If you have two subspaces, then their intersection is also a subspace. If you have two subspaces, then their union is not necessarily a subspace en general. This is the takeaway. Okay? You understand the two ideas that I've presented? C'est bon? Je passe? Très bien. Bien. Or at least in under 14 minutes, we can look at famille libre ou famille linéairement indépendante, which is also a concept that is extremely simple because we've already discussed une combinaison linéaire. We've already looked at une combinaison linéaire. We already know what that looks like. So let's look at the famille libre. So let's say we give ourselves a family of vectors V1, V2 and Vn de E. So est une famille libre C. So this family of vectors V1 up to Vn is going to be what they are calling une famille libre if for all scalars lambda 1, lambda 2 and lambda n, if the linear combination here, if the linear combination of these vectors, linear combination, remember, that's the key. If the linear combination of these vectors, V1, V2, and Vn is equal to 0, and if that implies that the coefficients lambda 1, lambda 2, up to lambda n are equal to 0, then this family of vectors is going to be libre. I'll repeat. We give ourselves a family of vectors. We give ourselves a family of vectors, V1, V2, up to Vn, if the linear combination, remember this is an implication. This is the proposition P, and then this is the proposition Q. How do we, prove an implication? If you're given, a problem to sort of like reason in this, reason based on what you're given here. You suppose that this is equal to 0. You suppose that P is true, and then you also show that Q is true. So here we suppose that the linear combination, if the linear combination is equal to 0, and if that implies that the coefficients lambda 1, lambda 2, and lambda jusqu'à lambda n are also equal to 0, then the family of vectors is going to be libre. Now, I'm not going to start with this example that is here. I'll pick a very simple example for us to work on. It's a very simple example for us to understand. Now, let's give ourselves a family of vectors. That's like the condition, that's like the definition is saying here. Let's give ourselves a family of what? A family of vectors. Now, let the first vector be, let's say we have V1. Let V1 be the vector 1, 0, 0. And then let V2 be the family 0, 1, 0, like so. And then let V3 be the family 0, 0, 1, like so. And then let's consider the linear combination of these two, the linear combination of these vectors. So we need scalars. So let's say I'm just going to call them alpha 1, alpha 2, and alpha 3. So these are elements of R in this case. So, in this case, our K is R. So let's take R like so. So let's show that this family of vectors is going to be libre. So let's show that this family of vectors is going to be what? Is going to be libre. Well, we look at the linear combination. So let's look at alpha 1, and we suppose that the linear combination is equal to 0. So alpha 1, and then we have 1, 0, 0, like so. Then plus alpha 2, 0, 1, 0, and then plus alpha 3, and then is 0, 0, 1, like so. We suppose that this is equal to 0. Now our goal, let's not forget our goal here, because it's very, very important. Let me write it in a different color so that we see that this is actually what we want to arrive at. Our goal is to show that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to 0. Now, that is our goal. So, let's simplify. So here we have alpha 1, 0, 0, like so, and then plus 0, alpha 2, and 0, and then plus we have 0, 0, and alpha 3, and then this is equal to, well, this 0 that is here, I can write it as the 0 vector, like so, 0, 0, 0, and then we add here. So here you have alpha 1, alpha 2, and then alpha 3, like so, is equal to 0, 0, 0, like so. Or two vectors are equal if and only if the corresponding components are equal. So it means alpha 1 is equal to 0, and then alpha 2 is equal to 0, and then alpha 3 is equal to 0. Now this is good information, because what this means is that the family of vectors we chose, v1, and then v2, and then v3, is going to be une famille libre. So une famille libre. Une famille libre. Because we started from this point, we started from here. This is our P. We supposed that the linear combination is equal to 0. And then we've shown that the scalars or the coefficients alpha 1 up to alpha 3 are all equal to 0. And so this has to be une famille libre. Now I'm going to leave the second one for you guys to try. I'm going to leave it for you to try. C'est très simple. You just have to choose 3 scalars since you have 3 vectors. So you can choose, for example, alpha. You multiply alpha by this one, you multiply beta by the second one, you multiply gamma by the third one. And then you suppose that the linear combination is equal to 0, and then solve the system of equations that you're going to have, and then vous aurez le résultat. Ok? C'est bon? Je passe? C'est bon? Right. Now that is great. So what we're going to do, since we have under 8 minutes, we'll exit this meeting, and then you guys are going to wait for the new link that I'm going to send, and then we'll continue. Okay, because we still have time. So let's continue. Let's keep going. So wait for the new link, and you can exit this one.